Relating macroscopic and microscopic definitions of entropy. We have given two different definitions of entropy change. The first is the macroscopic, in which the entropy change, delta S, is the integral of delta Q over T, where delta Q is the heat transfer and T is the temperature of the system. The second is the microscopic definition, in which delta S is equal to K ln of omega 2 over omega 1, where omega is the number of microstates of the system. How do these two definitions, macroscopic and microscopic, relate to each other? First, we need to discuss what we mean by the microstate of a gas. Quantum mechanics tells us that energies of individual molecules do not vary continuously. They occupy discrete energy levels. Now, for this discussion, we don't need to calculate the values of these energy levels. We're simply going to say that they will be denoted by epsilon 1, epsilon 2, and so on, all the way up to epsilon I. The number of molecules in any energy level, epsilon I, is Ni. So therefore, the total number of molecules in a gas, N, would be the sum of all of these Ni's. The total energy of the gas, U, would be the sum of Ni times epsilon I. Now, any arrangement of molecules that satisfies these two equations is a microstate of the gas. To explain this a little better, let's look at an example. So here we have a very simple system which consists of 5 molecules, so N is equal to 5, and the total energy of the system is 15. So here 2 of the molecules have energy 5, 2 of them have energy 2, and 1 has energy 1. You add them up, it gives you U is equal to 15. So this is a microstate of the system. Now, if the energy of any molecule changes, so the energy of one goes up by 1, then another one must decrease by 1. And so this again is another microstate in which the energy totals 15. If a molecule has an energy decrease of 3, then another one goes up by 3. And this is yet another microstate. So therefore, as the molecules jump from one energy level to another, the total energy must remain constant. We can show this in a simulation of a gas. So here we have a large number of molecules that are in a container. The average speed of these molecules is about 1400 meters per second. And that remains quite constant even as the molecules collide with each other and exchange energy. And if we look at the distribution of the speed and of the kinetic energy, we will see that those two are quite constant. There are small variations as the molecules collide with each other and with the walls of the container, and the energy changes, but overall the distribution remains quite constant. Now, this distribution is what is known as the Maxwell-Boltzmann distribution, and it can be calculated if we assume that all the microstates are equally probable. The Maxwell-Boltzmann distribution is a function of the temperature. So for a gas at 200 Kelvin, this is what the distribution looks like. Now, if we increase the temperature, the distribution becomes wider, which means that molecules are moving up to higher energy levels. Now, because they are moving up to higher energy levels, the number of microstates increases. So if the number of microstates omega increases, this means that the entropy of the system also increases when it is heated. We can look at simulations. And this is a gas which is now at 200 Kelvin. This on the right is a gas which is at 400 Kelvin. We can see that the average speed at 200 Kelvin is about 980 to 990 meters per second, while that at 400 Kelvin is about 1400 meters per second. The speed distribution also moves to the right because the average speed has increased. Consequently, the kinetic energy also increases, and the molecules are occupying higher and higher energy levels. This we can see by comparing the two simulations and the two kinetic energy distributions. Now, it is possible to calculate the number of microstates for a monoatomic gas. This is given by omega, which is a function of U, the internal energy of the gas, V, the volume, and N, the number of atoms in the gas. And it equals a function f of n times V to the power n times U to the power 3n over 2. Again, we don't need to go into the details of how we calculate this, but we are simply going to use this result for omega. Now we can take this function and use it to calculate the entropy of a monoatomic gas. So we take our definition of entropy, S is equal to K ln omega, and we substitute in that our expression for omega. We get that S, which is a function now of U, V, and N, is equal to K times ln of the function f of n plus n ln of V plus 3n over 2 ln of U. The change in entropy, delta S, which is S2 minus S1, will be equal to nk times ln of V2 over V1 plus 3 over 2 ln of U2 over U1. Note that that function f has now cancelled out, so we don't need to really evaluate that. This equation gives us the change in entropy delta S as a function of macroscopic variables alone. N, the number of molecules, V, the volume, and U, the internal energy. N times K we had shown is equal to N times Ru, where capital N is the number of moles and Ru is the universal gas constant. For a monoatomic ideal gas, we had also shown that the internal energy U is equal to 3 upon 2 nRuT. Therefore, the ratio of the final to the initial internal energy, U2 upon U1, is equal to T2 upon T1, because U is a linear function of the temperature. Let us take this expression for U2 upon U1 and substitute it into our expression for delta S. Delta S, therefore, is N times Ru into ln of V2 upon V1 plus 3 over 2 ln of T2 upon T1. We can use this expression now to evaluate how the entropy changes when we heat a gas at constant volume. So we have a gas in a rigid container at temperature T1. We heat it up until it finally reaches a new temperature, T2. Because the volume was constant, we can ignore the first term, ln V2 upon V1. Delta S, therefore, is equal to 3 upon 2 nRu ln of T2 upon T1. Heating the system, therefore, increases entropy. We can also look at the entropy change of a gas which is expanded at constant temperature. Here we have a container which is partitioned. Half of it is filled with a gas, the other half is a vacuum. We remove the partition the gas expands and fills the entire container. In this case, if we consider the entire container to be our system, when the gas expands, the boundaries of that system do not move, and so there's no work done. Therefore, the internal energy of the gas doesn't change, and its temperature is constant. So we can ignore the second term, 3 by 2 ln T2 upon T1. Delta S is equal to N Ru ln V2 upon V1. Therefore, free expansion of a gas also increases the entropy. We can use our expression for the total energy of the system, U is equal to summation of Ni times epsilon I, to evaluate the change in energy. So differentiating this expression, du would be the sum of Ni d epsilon I plus the sum of epsilon I dni. Now, the term d epsilon I would mean that we are changing the energy of each of our energy levels. dni would mean that we are changing the number of molecules in each level. Let us consider these terms one by one to try and understand what they mean. So here we have a gas which is at temperature T1, and the Maxwell-Boltzmann distribution at this temperature is shown. Now we heat up this gas until it reaches a final temperature T2. The Maxwell-Boltzmann distribution therefore expands out to the right because the molecules now occupy new energy levels. This movement of molecules to the new energy levels is what is meant by dni. We have changed the number of molecules in each energy level. The heat transfer, therefore, increases the number of microstates. So when we have heated it, we have increased the energy because molecules have moved up to higher energy levels. But in addition, we have also increased the entropy because they have occupied new microstates, and the total number of microstates in the system has increased. Now let's consider what we mean by d epsilon I. Here we have a container filled with gas, but instead of heating it, we exert a force on it and we lift it up to increase its potential energy. Now if we look at the Maxwell-Boltzmann distribution, the entire Maxwell-Boltzmann distribution moves to the right. So we have increased the energy of every energy level, but we've done it by exactly the same amount. So all the energy levels have increased by the same amount, and this would be d epsilon I. The work, therefore, does not increase the number of microstates. The number of microstates remains the same, but all of their energy levels have increased by the same amount. So if we do work on the system, the energy increases, but the entropy remains the same. So now if we go back to our expression for the total energy of the system, and we differentiate that to get du is equal to summation of Ni d epsilon I plus the summation of epsilon I dni, then this first term corresponds to the work which is done. The second term corresponds to the heat that is added to the system. We can therefore write du is equal to delta W plus delta Q. Delta W then is the energy transfer that does not increase entropy. Delta Q is the energy transfer that increases entropy. Finally, let us look at irreversible work. So here we have gas in a cylinder which is being compressed by a piston, and it is compressed very rapidly. Does this rapid compression increase the entropy? Now, if we have rapid compression, then the molecules don't have time to reach equilibrium and they will tend to accumulate near the piston. The molecules near the piston, therefore, will occupy less volume than those that are far away. To push a molecule into a smaller volume requires energy, which means that these molecules have been moved to higher energy levels than the ones that are far away from the piston. So therefore, their entropy is increased. Because the entropy of the system has increased, this is an irreversible process. On the other hand, if we have compression in a quasi-equilibrium process, then all the molecules are compressed equally. All of their energy levels are increased by the same amount, and therefore the entropy of the system remains constant. This is a reversible process. So rapid compression is irreversible work. Quasi-equilibrium compression is reversible work. Rapid compression or expansion generates entropy. Quasi-equilibrium compression or expansion do not generate entropy and are reversible. To summarize, microstates in a gas are defined by the energy level of molecules. The Maxwell-Boltzmann distribution gives the equilibrium energy distribution. As temperature increases, molecules shift to higher energy states, increasing the number of microstates. Adding heat to a system increases its entropy. Reversible work does not increase entropy, but rapid expansion or compression generates entropy.